Hello students, welcome to this particular session. In the previous session, we have discussed regarding polar dielectrics, non-polar dielectrics. We have discussed the concept of electric polarization, then dielectric strength, right? In this lecture, which is the continuation of the previous one, we will discuss about a dielectric slab of non-polar atoms when it is under the influence of external electric field, right? So students, suppose this is a dielectric slab of non-polar atom. This is a dielectric slab of non-polar atom. Of non-polar atoms. Now non-polar atoms means there is symmetrical charge distribution in each atom. It's perfectly spherical. So as a result, the center of gravity of the positive charge and the negative charge coincides. The center of gravity of the positive charge and the negative charge coincides due to the symmetric charge distribution. So each atom possesses zero dipole moment. Right? Each atom possesses zero dipole. Here the applied field is absent. So this is a dielectric slab of non-polar atoms in the absence of any external electric field. Each atom will have zero dipole moment. Each atom will have symmetric charge distribution, as a result of which the Cg of the positive charge and the Cg of the negative charge coincides. Right? Now, the same dielectric slab is made under the influence of this applied field. The same dielectric slab is placed under the influence of this applied field. So E0 is the applied electric field. Now students, we have discussed in the previous session, when a non-polar atom is under the influence of external applied field, then stretching of the atom will take place. The positive charge, it will experience force along the direction of the electric field. The negative charge, it will experience the same force but in the opposite direction. So the stretching of atom will take place. So the individual stretching or the stretching of the individual atom will take place. So what we mean to say is that the positive charge will experience force along the direction of the applied field, while the negative charge will experience force against the direction of the electric field. So the stretching will take place. So here I have shown it with the help of this diagram, right? So this is what the diagram will be like. So now it will be not spherical, it will be like this. So due to the finite separation between the center of gravity of the positive and the negative charge, each atom will develop its own dipole moment. So the dipole moment will get induced. So the positive charge will experience force along the direction of the electric field, while the negative charge will experience a force in a direction opposite to that of the electric field. So you can continue. So what I mean to say is that each atom individually gets stretched. So the stretching of the individual atoms under the influence of electric field does take place, right? So each atom will have some definite non-zero finite value of dipole moment. So as a result, this phase of the dielectric, here negative charge will get induced. Let us represent it by Qy. While on the opposite face of the dielectric, positive charge will get induced. Let us represent by Qy. And let us consider the thickness of the slab be D and cross-sectional area of the slab be A. Right? So look, I have stated the definition of dielectric. Do you remember, students? Dielectric is an insulator, a special type of insulator, which when placed under the influence of external field, opposite charges get induced on the two faces. Such a substance, such an insulator is known as a dielectric. It is due to electric polarization that these charges are induced on its opposite faces. Clear? So, as a result of these charges which get induced on its opposite faces, an electric field inside the dielectric is established. and obviously this direction is from positive to negative. So this electric field so developed due to these induced charges is known as electric field due to polarization. EP is electric field, it is electric field due to polarization. And as from the diagram it's pretty clear, the direction of the EP is opposite to that of the applied field. So obviously it is opposing the applied field. So the net field inside the dielectric will get reduced. So the net field inside the dielectric will get reduced and it will be given by E0 minus EP. This is a very, very important statement. So this E is the net field inside the dielectric slab and it is known as reduced electric field. It is known as reduced electric field. Fine. So E0 is the applied field, EP is the electric field due to polarization, which is present due to these charges which get induced on its opposite faces of the dielectric, and E is the net field inside the dielectric which obviously get reduced and is given by E0 minus EP. Obviously E0 is dominating one, it is the applied field, so the direction of the net field inside the dielectric will be along the direction of the applied field, right? So this is a very, very important statement. Also students, we need to discuss a very important term, polarization density. I will represent it by capital letter P, polarization density. Density means per unit volume, right? Polarization density. Now look, each atom under the influence of electric field will develop its own dipole moment. So the net dipole moment induced by the entire dielectric slab per unit its volume, that is known as polarization density, right? So suppose let each atom has dipole moment P. Suppose each atom develops a dipole moment P under the influence of this external field. Also, let N be the total number of atoms in the dielectric slab. Therefore, total dipole moment of this slab, it would be obviously N multiplied by P, isn't it? P is the dipole moment induced in each individual atom. And suppose this slab contains N such atoms. Therefore, total dipole moment induced in the entire slab would be Np. And polarization density, as per definition, is given by Np divided by volume. That is Np divided by P. P is the volume of what? Volume of this dielectric slab, which will be equal to cross-sectional area multiplied by this distance or thickness. So students, polarization density is the total dipole moment induced in the slab per unit its volume. Again I repeat, polarization density is the total dipole moment induced in the dielectric slab per unit its volume. So, what will be its unit? The unit of dipole moment, it is Coulomb meter. The unit of volume is meter cube. So, SI unit of polarization density is Coulomb per meter square. This is the SI unit of polarization density, right? It may also be written in this particular manner. It may be written as Np, where N is the number of atoms per unit volume. The SI unit of N would be per meter cube. It is known as the number density of the atoms. Number density of atoms means number of atoms present per unit volume of the slab under consideration, right? So this is another important thing. Now coming back, there is a term, atomic polarizability and electric susceptibility. Let's discuss those terms as well. Now it is found that the dipole moment induced in each individual atom is found to be proportional to the net electric field inside the slab. That is, it is found to be proportional to E. Now in order to eliminate this proportionality sign, we need to introduce some constant, and that constant is alpha epsilon E. This is the proportionality sign and this is alpha. This alpha is known as atomic polarizability. It is known as atomic polarizability. You can find its SI unit. It would be actually, let's find it. Alpha is equal to P divided by epsilon E. Let's check it out. The SI unit of P, it's coulomb meter. Epsilon, it is coulomb square per Newton per meter square. Electric field, it's Newton per coulomb. Newton per Newton get cancelled, right? Per coulomb, C1, C get cancelled. So, we'll get meter cube. So, atomic polarizability has got the same dimensions as that of volume. So, the SI unit of alpha is meter cube. So, its dimension formula would be L3. It will be having the same dimensions as that of volume, right? So, this was regarding atomic polarizability. Also, it is found that the polarization density is found to be directly proportional to the net field inside the dielectric slab. Net field inside the dielectric slab. What I mean to say is that also this polarization density, capital P, is found to be the net field inside the dielectric slab, that is proportional to E. Again, in order to eliminate this proportionality sign, we need to introduce some constant. This constant over here is chi, this is chi, C-H-I, chi, epsilon E. It is known as electric susceptibility. This term is known as electric susceptibility. Electric susceptibility. We will discuss about this term susceptibility theoretically in the subsequent chapters in magnetism, right? When we discuss about magnetic susceptibility, right? Susceptibility actually is the allowance of the field lines or the acceptance of a medium to make the field lines pass through it. That is susceptibility. Prone, aptness, right? So that is electric susceptibility. Now, this is another important expression. Also, we have discussed this. Just now we have discussed N into P. Also, we have discussed P is equal to alpha epsilon E. So, with the help of these three relations, we can easily determine the relationship between atomic polarizability and electric susceptibility. So let's do it. It's a relation important from comparative point of view, basically. So let's solve it as P is equal to NP. So in place of P, we can write chi epsilon E. This is chi, C-H-I, chi. It denotes electric susceptibility. Susceptibility, right? And it is equal to N. N is the number density of atoms, and small p, just now we have discussed, it's alpha epsilon E. Alpha is the atomic polarizability. So therefore, this is the relationship between electric susceptibility and atomic polarizability. Remember students, N is the number density of atoms, which is the number of atoms per unit volume, right? So what is the SI unit of chi? Its unit is per meter cube. Its unit just now we have discussed it's meter cube. So meter cube per meter cube get cancelled. So chi is a dimensionless quantity. Dimensionless quantity with no unit. It is a dimensionless quantity having no unit. So that's electric susceptibility. So this is the relationship between atomic polarizability and electric susceptibility, right? Susceptibility means how prone a medium is towards the effect of electric field. So that's susceptibility. We'll discuss it in detail in the subsequent chapters. Now coming back to polarization density. Now look. Polarization density, as there is some alternative form of representing this polarization density. So let's discuss alternative expression for polarization density, right? Polarization density, theoretically, as I have told you, it is the net dipole moment induced per unit volume. So what I mean to say is that, what is the dipole moment induced? Net charge induced over here is minus Qi, net charge induced over there is Qi. And net dipole moment, you are aware, product of magnitude of either of the charge and the distance between them, which is d. So this is the net dipole moment induced in this slab. Per unit its volume of this dielectric slab, right? So polarization density, capital P, it's QID divided by volume. Volume is cross sectional area. Suppose this is the slab. So this is the cross section area I am talking about. This is the cross section area. So cross section area multiplied by the thickness, that will give you the volume of the slab. So capital P is equal to QI divided by A. Clear? So this is induced charge per unit area of the dielectric slab. It is known as polarization charge density, represented by sigma P. Sigma P, you are aware, it's the surface charge density, charge per unit area. This is also surface charge density due to the induced charges. The induced charges per unit area, that is polarization charge density. So both are same. Polarization density or sigma P, it's the same thing. Clear? So this is another alternative expression for polarization density. Again, there is some other important aspect as well. There is a term called dielectric constant. Dielectric constant. Now, this is represented by K. We have discussed it earlier as well. It is also known as relative permittivity of the medium. Now, in this context, when a dielectric slab is under the influence of external electric field, the dielectric constant of the dielectric slab is defined as the ratio of the applied field, this is the applied field, to the reduced electric field. That is the net electric field inside the slab. So, dielectric constant, right? It is represented by capital K. Dielectric constant of a dielectric slab under the influence of the applied field is defined as the ratio of the applied electric field to the reduced electric field. So, being the ratio of two similar physical quantities, it is a dimensionless quantity. It may also be written as E naught divided by E is E naught minus EP. E naught minus EP. So, this is another very important expression for dielectric constant. Here I must mention, for conductors, in case of conductors, if we replace this dielectric with a conductor, we are aware inside a conductor the net field is 0. So inside a conductor the net field is 0. So this will become 0 in case of conductor. So K will become infinite. So students, remember, this is a very important concept. The dielectric constant of a conductor is infinite. For vacuum it is 1, and for any other insulator it should be greater than 1 and less than infinite. Is it clear? So this is regarding dielectric constant. Now let's find out the relationship between K and chi. This is the dielectric constant and this is the electric susceptibility. So let's find out the relation between dielectric constant and electric susceptibility. So we'll begin with this step. When a dielectric slab is under the influence of external electric field, then the net electric field inside the slab gets reduced, and it is given by E is equal to E naught minus EP. Now EP, it is the electric field due to polarization. Due to polarization, the surface charge density is sigma P. We are aware electric field in this space between the plates is sigma by epsilon. Here in place of sigma we will write sigma p. It is due to polarization. This is electric field due to polarization. So electric field due to polarization would be sigma p, which is polarization density divided by epsilon naught. Isn't it? So further we get sigma p is polarization density, capital P. Still further, we can write it as P. It's given by chi epsilon E. Just now we have discussed. Right? This is chi, electric susceptibility. Since polarization density is chi epsilon E. This is polarization density. So that is what I have substituted the values over here. So epsilon get cancelled. So what do we get? E is equal to E naught minus chi E, or E 1 plus chi is equal to E naught. Therefore 1 plus chi is equal to E naught divided by E, which is equal to K. E naught by E is equal to K. So students, what is the relationship between dielectric constant and electric susceptibility? It is K is equal to 1 plus chi. So the relationship between dielectric constant and electric susceptibility is K is equal to 1 plus chi. This is the relationship between electric susceptibility and dielectric constant. So these are some very, very important topics. You need to be thorough about whatever you are studying. Don't miss a single topic. Right? Do every topic in detail. So I hope you have understood these topics. What we have done in this session is, we have discussed when a dielectric slab of non-polar atoms is under the influence of external electric field. So we have discussed the concept of electric field due to polarization. We have discussed the concept of reduced electric field. We have discussed the concept of dielectric constant of a dielectric slab. Then we have discussed electric susceptibility, atomic polarizability. Then we have discussed various expressions for polarization density, right? And eventually we have discussed the relation between electric susceptibility and polarizability, and also the relation between dielectric constant and electric susceptibility, along with their units and dimensional formula, right? So students, do thoroughly revise this topic and we'll continue in the next session.